Tonight, we drift alongside a quiet traveller from another star, interstellar comet 3I Atlas. Discovered in 2025, it's gliding through our solar system on a one-time visit. No threat, just a rare, serene encounter. The James Webb Space Telescope has already taken a close look, and what it found shocked astronomers. An unusually carbon dioxide-rich breath of gas, water ice shimmering in the dark, and a lopsided sun-facing exhale. Settle in, slow your breathing, and let's follow this visitor's peaceful path. Imagine looking up into a cool, clear night and knowing that one of those tiny moving sparks is not from here. Not from our sun, not from our ancient family of planets, but from somewhere beyond, another stellar neighbourhood entirely. That is what makes 3I Atlas so quietly astonishing. It is an interstellar visitor, travelling on a path that doesn't loop back like the comets born in the outskirts of our own system. Its course is open-ended, a soft arc that will never close. It will pass by, whisper its message in light, and continue on into the dark, carrying the memory of another sun. Interstellar simply means between stars, and for an object like this, it's both a description and a journey. Most comets we see are long-period wanderers that still belong to the Sun. Their orbits are stretched and slow, but they are bound. If we could be very patient, thousands, even millions of years, those comets would return. This one will not. Its trajectory is hyperbolic, which is a calm mathematical way of saying it's a guest, not a resident. Gravity curves its path but cannot hold it. Like a traveller who pauses at a window to watch the lamplight and then moves on, it is just visiting. You can picture the story that likely sent it our way. Far in another system, long before our species learnt the names of constellations, a small icy body formed in the cold outer reaches around a different star. There, giant planets, still young and unsettled, tugged and nudged their surroundings. One strong encounter, just the right pull at just the right time, was enough to eject a small frozen world into the open sea between stars. It may have wandered for millions of years through an invisible landscape of thin gas and starlight, slowly darkening as radiation baked its surface, until chance and geometry brought it near our sun, where its long sleep would end in a brief moment of brightness. Even before any images appeared, the way astronomers knew this object was special came from how it moved. A faint point of light, measured night after night, does not keep secrets for long. Plot those positions carefully, fit them to an orbit, and the nature of the path reveals itself. When the numbers show a speed and curve that cannot be captured by the sun's gravity, the conclusion is simple and beautiful: interstellar. That single word changes everything. It means we are not just watching an icy time capsule from our own beginnings, we are looking at a package delivered by another nursery. The name tells its own story. 3I marks it as the third confirmed interstellar object we've witnessed, following the first enigmatic visitor and the second more comet-like traveller that came after. The Atlas part honours the survey system that noticed it, the quiet, tireless skywatchers that scan each night for moving points, changes in brightness, and subtle motions that would escape the human's eye. It's easy to imagine rows of telescope domes under a silent sky, catching a fleeting pattern in the noise and flagging it for a closer look. In that way, the modern sky is like a gently humming net. And now and then it finds something rare. Knowing that it is interstellar brings an immediate question. How close will it pass, and is it safe? The answer is softly reassuring. This is a distant passage. In the months around its closest approach to the Sun, 3I Atlas brightens as sunlight warms its surface, releasing gases and dust that form the delicate envelope we call a coma, and perhaps a thin tail pointing away from the Sun. But its path keeps it well away from Earth. It is not a threat, only a spectacle. A lantern moving along the far edge of the lake, its reflection rippling as it goes. There is a gentle rhythm to how such a visitor changes. At first, when it is far out and cold, it looks like a star that slides slightly between frames. Then, as it drifts deeper into sunlight, The ices locked in its crust begin to sublimate, turning directly from solid to gas. Gas carries dust. Dust softens starlight, and the point becomes a halo. That halo is not uniform. Small patches on the surface, sunlit, afternoon slopes, pits and cracks, wake up first, exhaling into space. Those breaths imprint a subtle asymmetry, a lopsidedness that tells us where heat is doing its work. For astronomers, that uneven glow is not a flaw, it's a map, a way to read the surface without ever touching it. Because it is interstellar, the chemistry of this coma matters more than usual. It is the closest we may come for now to sampling the building blocks from another system's pantry. Different stars, different disks of gas and dust, different distances from their heat. These ingredients shape comets in different ways. Some may be rich in certain ices, others poor, some may carry complex carbon chains, others just simple volatiles. By measuring the light and splitting it into spectra, thin fingerprints across the infrared, astronomers can tell what is escaping. Water, carbon dioxide, carbon monoxide, and other quiet participants in the story of worlds. Every ratio hints at a place of origin, closer to heat, farther from it, processed by the radiation differently across eons. It helps to remember how much coordination it takes to greet such a traveller. Robotic surveys flag the motion. Observatories around the world pivot to track it, trading night for night as the Earth turns. Radio, optical, and infrared instruments all contribute notes to a shared score. As it brightens and fades, as its angle changes and the tail shifts, the pattern becomes a time-lapse of behaviour. How quickly it responds to sunlight, how much dust it sheds, whether it flickers with bursts from active vents or remains calm. This chorus of data doesn't just describe a single comet. It anchors comparisons among all three interstellar visitors we've met so far, letting us see the diversity of other planetary systems through small icy messengers. What makes the moment special is its unrepeatable nature. Long-period comets might return after an age. This will not. Once it arcs past the Sun, its speed and the geometry of its approach send it outward again, diminishing steadily until it is once more a star-like mote, then gone, on its way to nowhere in particular and everywhere at once. We will keep the records, the careful measurements, the quiet plots, the spectra sewn with tiny lines. We will keep, too, the feeling that arrived with the first announcement. That small shiver of perspective that comes from knowing we are part of a larger exchange, a slow conversation across the distances between suns. For now, though, it is enough to imagine its motion through our sky. Somewhere above the horizon, in the patient dark, 3i Atlas slides a little each night against the background stars. It does not rush, it does not burn, it simply continues, exactly as it has for ages, altered only by the nearness of a single star among many. If you listen closely, you can almost hear the soft logic of celestial mechanics guiding it along, a steady, comforting certainty. In that certainty, there is room to breathe. There is room to rest. Think of this encounter as a quiet boat gliding along the far side of a moonlit lake. You can see the ripples it makes. You can admire the glow on the water, but it never comes near your shore. That's 3i Atlas, present, observable, and moving through our neighbourhood, yet keeping a respectful distance from Earth. There's a gentle comfort in that. We get the wonder without the worry. When astronomers call its path hyperbolic, they are describing more than a curve on paper. It's a declaration of freedom. A bound comet loops back eventually. A hyperbolic traveller bends a little in the sun's gravity, and then sails on forever. That shape guarantees a safe passage. Gravity is like a hand that guides but doesn't grasp, enough to change the direction, not enough to capture or pull it dangerously inward. The energy of the object is simply too high for the sun to hold. So while it brightens for a short season as it approaches, it remains a distant light, making its turn in the inner reaches of our solar system and then slipping away again. Distant doesn't mean dull. Safety here is a kind of stagecraft. The comet performs under the lights without stepping off the proscenium. As sunlight touches its surface, frozen gases begin to lift, carrying dust into a glowing halo. That halo, or coma, is like a lantern's soft glass, illuminating the object while also masking its solid heart. From our perspective, the tail unfurls not behind the comet's motion, but away from the sun, shaped by sunlight and the solar wind. It's a common misunderstanding that tails trail the path like smoke from a train. In truth, they point outward from the heat source, like a long, pale windsock. Even as 3I Atlas rounds its closest approach to the sun, that tail continues to declare its distance from us, streaming into space along lines sculpted by light. There's a second layer to SAFE, the dynamics of space traffic. Earth and the comet occupy different lanes and different speeds. The geometry of their meeting is all angles and timing, and the timing here is not the sort that brings two bodies together. If you picture the solar system as a slow orchestrated dance, this is one of those moments where partners cross the floor on separate steps, close enough to acknowledge each other, far enough to avoid even a brush of sleeves. For astronomers, that spacing is a gift. It lets telescopes observe the comet's behaviour over many nights without dealing with the complications of rapid close motion. Because it stays far off, there are no tidal effects for us to worry about, no disruptions to satellites, no atmospheric displays that demand alarms. The encounter is purely observational. The biggest impact it has on Earth is the way it nudges our curiosity awake and sends observatories into a coordinated routine, pointing, tracking, measuring, and comparing notes. That coordination is its own kind of reassurance. We know where the visitor is, we know where it's going, and we know it will continue outward once its brief warming fades. If you visualize the journey, imagine a wide, shallow arc that dips towards the sun and then rises away again. At first, while it's far and cold, the comet is just a point that slides slightly each night against the patterned background of stars. Then, as the sunlight increases, a soft haze appears around that point. The coma brightens, textures emerge in long exposures, and a tail begins to sketch itself into the darkness. All of this unfolds at a comfortable remove, like watching distant weather on the horizon, a display of nature that's grand and intricate yet not headed your way. There is also the matter of brightness, which tells a gentle story of distance. An object that never comes close must do its glowing from afar. For most sky watchers, that means 3I Atlas is a telescopic treat rather than a naked eye spectacle. That's perfectly fine for a sleep-friendly documentary. It nudges us toward a softer sort of awe, one that relies on imagination and patient images from the world's instruments. We trade fireworks for detail, spectra that reveal chemistry, time-lapse sequences that show how the tail breathes and shifts, and careful measurements that map the subtle curve of its flight. It's the kind of beauty you sip rather than gulp. Safety, too, is about predictability. Once the orbit is measured over many nights, astronomers can project its future positions with calm confidence. The uncertainties shrink, the ephemeris, the nightly almanac of where to look, settles into place. There's something soothing about that steady refinement. Each new observation is like a stitch, tightening the weave of knowledge until the path is not just guessed but known. And because the object is interstellar, that knowledge carries a touch of poetry, a precise map for a traveller that will never return. Consider what closest approach means in practice. For a comet passing far from Earth, the moment it's nearest to the Sun is not the same as the moment it's nearest to us, and neither is especially near. The comet's gentle bow around sunlight happens in its own lane, at a distance that keeps it a celestial neighbour rather than a visitor to our doorstep. We are spectators from the garden, not hosts in the foyer. And that distance helps in another way. It prevents extreme activity from overwhelming our instruments, allowing a cleaner readout of the gases and dust drifting off its surface. Even the tail's behaviour whispers no hurry, no harm. As the comet rounds the sun and begins to recede, the tail reorients to continue pointing away from the sunlight. the whole display gradually dims, not with a snap, but like the slow fade of stage lights after the final line. Dust lingers along the path like a delicate footprint, then thins into invisibility. All the while, the solid nucleus, small, dark and unthreatening, continues outward, back into the deep where starlight is only a thought. From a human point of view, there's a lesson tucked inside this safe, distant passage. Not every dramatic thing needs to be close to be meaningful. Some wonders are best appreciated with space around them. With 3i Atlas, that space is literal and figurative. Kilometers between worlds, and also a comfortable margin for our thoughts. We can linger on the implications, what its chemistry says about the star system that made it, what its unusual behaviour suggests about how comets vary across the galaxy, without the urgency that proximity brings. It's a study in calm attention. If you step outside on a clear night during its time in the inner solar system, you won't feel anything unusual in the air. No wind will change, no animals will grow restless, no tides will surge, and yet above you, in a geometry too vast to sense directly, a visitor from another sun will be passing through, quietly, politely keeping its distance. Somewhere a telescope will be following it, and somewhere else a spectrograph will be turning its light into tiny fingerprints that scientists can read like a diary. Those efforts will leave us with charts and images and plots, evidence of a moment when two star system stories brushed lightly in the dark. Before the first image ever appears, there is the hush of careful preparation. Far from Earth, folded into the cold shade of its great silver sunshield, the telescope turns its honeycomb eye, not all at once, but with the graceful precision of a dancer finding a familiar pose. Commands that began as quiet keystrokes on the ground arrive as pulses of intent. Gyros ease, reaction wheels whisper. The observatory settles into a posture that keeps the sun, earth and moon safely behind the shield while opening a window toward the faint traveller. In that window, a point of light is moving ever so slightly against the fixed pattern of stars. To follow a wanderer that does not sit still, the observatory has to do something special. It practices a kind of celestial empathy. On board, the fine guidance system locks onto a steady guide star, and then, using a living timetable built from the comet's predicted positions, it applies tiny continuous nudges so that the instruments drift with the comet's motion. The math that feeds those nudges is prepared long beforehand, ephemerides computed, uncertainties tamed by the nights of tracking from the ground. When the time comes, the telescope does not chase. It simply moves as if it were already riding along. Now the instruments wake in sequence. A camera frames the field to confirm that the visitor is exactly where it should be, and then the spectrograph takes its seat at the front of the class. Spectroscopy sounds technical, but its heart is simple. It turns light into language. A prism or grating spreads the comet's glow into a soft rainbow, and within that rainbow are tiny dark and bright features, lines and bands, each one a syllable from a particular molecule. Water speaks in one place, carbon dioxide in another, carbon monoxide somewhere else. Dust adds a warm continuum, a gentle pedestal of reflected sunlight and thermal glow. The spectrograph listens to all of it at once. Because the comet is faint and changing, the team chooses settings with care. A low-resolution mode gathers the broad story quickly. A wide sweep across the near-infrared, where the most telling fingerprints live. Then, if time allows and the signal is strong, a higher resolution mode refines the details, separating neighbouring lines that would otherwise blur together. To catch not only a line of light but its shape in space, the instrument can use an integral field unit, a tiny box that slices the scene into many adjacent slivers, each with its own spectrum. When the data are stacked, you can make a little cube, 2 dimensions of place, 1 of colour. It's a map and a chemistry set in one. Pointing at a moving, breathing ice rock isn't as simple as holding still and collecting. The observatory gently dithers this target, stepping it by small amounts between exposures to average out detector quirks and cosmic ray hits. It watches the background too, the faint grain of zodiacal light, the dark current of the sensors, the stray ghosts that can appear when bright stars are nearby. All of that must be understood and removed so the comet's whisper doesn't get lost under the room's hum. A pattern of exposures, offsets and calibrations is choreographed like a slow waltz, precise and repeatable, unhurried and kind. Inside the electronics, each exposure begins as a field of numbers, counts of photons that have walked through mirrors and slits to arrive on the detector. Those raw frames are not something you would hang on a wall. They need the patient work of a pipeline that has learned the instrument's personality, how to subtract the bias and the dark, how to flat field away uneven sensitivity, how to assign a wavelength to every pixel, and how to turn counts into physical flux. To be sure the colours are true, the instrument compares against known lamps and trusted stars. Only when the housekeeping is complete does the comet's spectrum show itself with clarity, like handwriting brought into focus. And then, across the calibrated plot, brightness versus wavelength, appear the signatures that turn a moving dot into a living object. A broad swell betrays warm dust reflecting sunlight and radiating heat. Fine ridges and notches mark the presence of specific gases boiling off the surface and into space. In the near-infrared, water's low vibrational lines curl up like delicate threads. Carbon dioxide leaves a strong, unmistakable imprint. Carbon monoxide whispers nearby. The relative strengths of these features tell you which ices are waking first, which are shy, and which dominate the exhale. Even the shapes of the lines can hint at temperature and the speed of the escaping gas. Because a comet is not a smooth sphere but a landscape, pits, cliffs, and sunlit slopes, its outgassing is not uniform. One side may wake before the other. In the spectra and images, the unevenness appears as a slight lopsided glow, a sunward brightening, a tail that begins to draw itself outward along the invisible push of light. If the integral field unit is used, you can walk through the data slice by slice and watch where certain molecules are densest, how they thin with distance from the core, and whether there are hints of jets, narrow streams from active vents, that paint the coma with a subtle structure. All the while, the observatory keeps its calm. The sunshield sheds heat like a silent curtain. The mirrors hold their figure with picometer pride. The segmented eye acts as one. The star trackers and gyros keep the motion so smooth that the spectrum stays sharp and centered, even as the target slides across the sky at its own small pace. If a tiny correction is needed to keep the nucleus aligned within a narrow slit, the system makes it without fuss. Hours pass in this quiet way. The work is invisible, and that is how you know it is good. When the observing window closes, either because geometry demands a pause or because the plan has been fulfilled, the data make their way home. On the ground, the team stretches, smiles, and begins the tender art of interpretation. They compare nights, watching how the features grow or fade as sunlight changes. They compute production rates, how many molecules of water, how much carbon dioxide, how much carbon monoxide are leaving the nucleus each second. They compare these ratios to those seen in other comets, and they ask what this mix suggests about the place where this traveller formed. Closer to its native star? Farther, bathed in different radiation, processed differently over eons of interstellar drifting? Images from the camera become the comet's portrait gallery. The size and shape of the coma, the length and angle of the tail, the way dust reflects and scatters the light. If the nucleus is bright enough to peek through, they bracket its size. If not, they set limits. Time-lapse sequences reveal subtle breathing, small brightenings after a patch turns into sunlight, small relaxations as it turns away. Even without drama, the rhythm is there. Day and night on an object no human will ever stand upon, a slow rotation measured only by changes in light. Every element of the observatory's design plays a role in making this softness readable. The cryogenic cold keeps thermal noise low, so faint signatures are not drowned out. The large mirror gathers enough light that short exposures can be stacked, preserving resolution while protecting against saturation. The freedom from Earth's atmosphere eliminates the swaying, absorbing and glowing of air, letting delicate infrared features stand in clear relief. All of this allows a sensitivity to chemistry that ground-based telescopes struggle to reach, especially for gases like carbon dioxide that the Earth's air hides from view. And so a quiet miracle occurs. A point of light that would once have been only a curiosity becomes a story with characters and motives. The spectrum speaks of birthplace and journey. The images speak of activity and surface. The timing speaks of rotation and sunlight's touch. The fact that this comet is interstellar turns every conclusion into a postcard from another nursery, another disk of gas and dust, another set of distances where different ices can form and survive. Even the unexpected and imbalance here and absence there becomes a clue instead of a contradiction. When the telescope finally turns to its next task, the afterglow is not on the sky but in the data. There, line by line, is the memory of a visitor passing through, the breath of ices warmed by a new sun, the shape of a coma moulded by light. Nothing exploded, nothing rushed. And yet, in the hush, something profound happened. A different star system, through an emissary of ice and dust, told us a little about itself. You don't need to hold the spectrum in your hands to feel the comfort of that. It's enough to imagine the golden eye opening, the faint rainbow unfurling, and the story, patient, precise and kind, writing itself across the dark. Imagine the telescope's spectrum as a quiet page of music, and on this page a single instrument begins to play louder than expected. That instrument is carbon dioxide. In most comets we study close to the sun, water tends to carry the melody. It turns on strongly as sunlight warms the surface and its vapor dominates the faint atmosphere, the coma, that forms around the nucleus. Here, though, the notes from carbon dioxide stand up clear and tall. They arrive in the near-infrared as unmistakable features, the kind that even a tired scientist blinking at a midnight monitor can recognize. The breath of frozen CO2 turning to gas, drifting outward, and telling us a story about where this traveller came from and how it's waking up now. Why is that surprising? Because carbon dioxide is more volatile than water. It needs less heat to sublimate, so it can drive gentle activity while a comet is still far from the sun, sometimes long before water gets involved. With most Earth-based telescopes, CO2 is frustratingly difficult to measure directly. Our own atmosphere is full of it, hiding the telltale wavelengths and blurring the signal. From space the view opens. The spectrum that unfolds shows carbon dioxide's signature cleanly, and beside it, the places where water would normally announce itself. In this visitor, the balance tilts. The CO2 lines don't just whisper, they speak with confidence. That balance carries clues. Think of a protoplanetary disk, the birthplace of comets, as a vast pantry with shelves marked by temperature. Close to the star, only the most refractory solids can survive. Move outward and you pass ice lines, regions cool enough for various vapors to freeze. Water condenses closer in. Carbon dioxide, being more volatile, prefers a colder shelf farther away. If a comet's coma shows unusually strong CO2 compared to water, one straightforward interpretation is that the comet formed or spent much of its early life out by that colder shelf, stocked by a different recipe than the one that shaped many of our local comets. In other words, the spectrum is not just chemistry, it's a map of childhood. But nature is generous with possibilities, and the telescope's job is to help us sort them. A CO2-rich exhale could also reflect what the surface has experienced since the comet was born. As small bodies wander, they're slowly altered. Their outer centimeters can be cooked by past sunlight or bleached by cosmic rays, leaving an insulating crust of dust that hides deeper ices. If the very top layers have already lost much of their water through repeated warming in another star's system, or even during a previous distant past near our sun, then fresh sunlight now might release more CO2 than H2O at first, simply because the CO2 sits closer to the surface, or because it's trapped in a kind of glassy, amorphous water ice that releases it in spurts when the structure warms and rearranges. What looks like more CO2 than water could be a timing story. Which cupboard door opens first as the day begins? Geometry matters too. A comet is not a smooth billiard ball, it's a landscape. Pits, cliffs and shadowed alcoves create microclimates. Sunlight arrives from a particular direction, warming some patches while leaving others asleep. If the active regions that catch the first light happen to be CO2 rich, the whole coma takes on that character, at least for a while. As the comet rotates and the seasons of its brief visit unfold, different patches wake up. A spectrum taken on one night is a single frame in a slow-turning film. It tells the truth of that moment and invites us to keep watching. This is why the observatory's sensitivity at specific wavelengths is such a gift. In the near-infrared, there are places where water announces itself, and places where CO2 sings. The instrument can separate those voices, measure their relative loudness, and track how the duet changes over hours and days. If we see the CO2 features hold steady while water gradually grows, then we learn about the depth of the thermal wave, how far heat is penetrating, and about the layering of ices beneath the surface. If both rise in step, we learn something else, that the same patches may be driving both, or that fresh material has been exposed maybe by a small landslide, or we are a gentle outburst. Even the shape of each spectral line is a clue. A broader line can hint at warmer gas or faster expansion. A slightly shifted line can reflect the bulk motion of the coma along our line of sight. By fitting these shapes carefully, scientists can estimate temperatures and speeds, and then fold those numbers into models that predict how much gas is being released every second. Those production rates become the language we use to compare this visitor to others, not just strong or weak, but how strong and how does it change. It helps to place this CO2 forward behaviour in context. The few interstellar visitors we've studied already hint at variety. One with a little obvious coma at all, another that looked more like a familiar long-period comet, and now this traveller with a distinctive chemical accent. In our own solar system, comets display a wide-spreading carbon dioxide relative to water. Some are modest, some are robust. What makes this case special is not that CO2 is present, but that it's taking over a stage so clearly during the window we can observe, and that the object carrying this pattern comes from another star. The combination turns a routine measurement into a cross-galactic comparison. Of course, a careful team resists the urge to declare a permanent identity from a single night spectrum. They return, they repeat, they watch the ratio evolve, they compare the amount of dust to the amount of gas, since dust is the stage on which the gases perform. Grains can insulate ices, grains can clog vents, grains can carry embedded ices away where they sublimate later, at a distance from the nucleus, changing the apparent chemistry as a function of radius. With integral field observations, they can literally map the coma in both space and colour, watching where CO2 is densest, how quickly it thins, and whether the water follows the same pattern or traces a different path. These two gases do not always share the same sources. A crack rich in one can sit meters away from a crack rich in the other, and the coma will remember. From a formation point of view, the implications are delicious. If interstellar comets often show strong CO2, maybe many planetary systems build icy grains in colder zones, or perhaps their giant planets tend to scatter material from those zones more efficiently. If instead this traveller is an outlier, then its spectrum becomes a rare postcard from an unusual nursery. A system where the carbon chemistry, the disk temperature profile, or the history of irradiation favoured storing more CO2 in cometary ices. Either way, the result sharpens our models of how solids grow, migrate, and get ejected, turning abstract diagrams of disks into living, testable pictures. There is a practical sweetness here too. Because carbon dioxide is so hard to isolate from the ground, even for bright nearby comets, space-based measurements become a kind of anchor. They calibrate our expectations and help interpret other indirect traces. When we see certain dust colours or certain emissions that correlate with CO2 in spaceborne spectra, we can look for those proxies from Earth when the space telescope is busy elsewhere. In that way, one quiet interstellar visitor improves how we read many comets, not just itself. And then there's the human part. Somewhere, a grad student has watched those CO2 features rise on a screen and felt a jolt, not of alarm, but of recognition. The pattern matches the one in a textbook plot they once traced with a finger. The difference is that this time the plot comes from a traveller between stars. Someone else, experienced and steady, glances at the water bands and hums, lower than expected tonight. They both know better than to fall in love with a single snapshot, yet both allow themselves one long breath of satisfaction. It's rare to catch the universe being so articulate. As the days pass, the story will complicate in the best way. Water may strengthen or not. Carbon monoxide, more volatile still, may trace an even colder reservoir. The dust production may rise and fall with the rhythm of rotation, revealing which longitudes wake the strongest. But the first clear lesson will remain. This comet's coma is rich in carbon dioxide. And that richness is a key to its origin and behaviour. It tells us that somewhere, around a different sun, there is or was a zone where CO2-laden grains formed and gathered, and that some of those grains grew into a body sturdy enough to travel the gulfs between stars. When you close your eyes, you can imagine the scene without numbers. Picture a dark, uneven surface turning slowly in unfamiliar sunlight. From sun-touched slopes, colourless vapour rises, carrying fine dust into a soft halo. One kind of vapour is eager. It has been waiting for less warmth than its neighbour. It goes first, confidently shaping the coma's character. Instruments far away, cold and patient, write down each breath as a line on a spectrum. From those lines, a simple truth emerges with calm authority. Here, now, carbon-borne dioxide leads the song. And in that gentle, unexpected melody, we learn a little more about how worlds begin. First comes the hush of sunlight touching a frozen surface that has never felt this star before. Think of a dark, uneven crust, pitted and cracked like old pottery, turning slowly as it approaches the warm side of space. On the sunlit slopes, the first grains glimmer. Hidden within that crust are pockets of water ice, some crystalline, some still in a glassy amorphous state, locked away in pores and veins. As warmth seeps a few centimetres down, those pockets begin to stir. Molecules loosen, pressure gathers in tiny chambers, and then gently the surface exhales. From a distance, that exhale appears as a soft brightening on the side facing the sun. It isn't dramatic, it is persuasive. The coma, the comet's delicate atmosphere, puffs into being, thicker where the daylight works first, thinner where darkness still holds. Instruments tuned to the near-infrared listen to the quiet change, and the fingerprints of water vapour appear as thin, repeating lines, like finely spaced strings on a harp. Between those lines, the continuum of reflected light carries another secret, the unmistakable imprint of water ice mixed with dust, tiny dips and textures that say, yes, true ice is present, not just vapour. Ice and gas together, the solid and the breath. The reason the glow tilts sunward has as much to do with landscape as with light. Comets are lumpy, stitched from ancient rubble. A cliff catches daybreak before a neighbouring hollow. A ridge throws a long morning shadow over a pit that won't wake until later. Where sunlight lingers, water trapped near the surface warms enough to sublimate, and the gas pushes outward, carrying dust with it. The flow makes a fan, not a perfect sphere, a soft, sun-facing plume that thickens the coma on one side. If you could stand above the nucleus and watch, you would see curtains of vapour rising from certain longitudes as they turn into daylight, like slow white flags unfurling and then relaxing again at night. There's a choreography to the gases. Carbon dioxide may have started the dance earlier, eager and volatile, but water joins as the heatwave sinks slightly deeper into the crust. Some of that water arrives directly from sun-warmed surfaces. Some arrives indirectly. Grains lifted off the nucleus that carry frozen water within them. Grains that continue to warm as they drift, releasing vapour at some small distance from home. That second path, sublimation from icy dust, can create a halo within a halo, a place where the water signature grows stronger just off the nucleus, shaping the coma's texture in a way instruments can map like weather. Look closely and you can feel rotation at work. The nucleus turns, presenting a new patch to the sun, turning an active jet away while another wakes. Brightness swells and ebbs with a patient rhythm, hours, not minutes, like the rise and fall of breathing in sleep. Each active region has its voice. One patch releases gas in a broad sigh. Another produces a narrower jet that paints a faint streak through the inner coma. Another sleeps through dawn and stirs only at local noon when heat is soaked in. Over time, these patterns draw a subtle asymmetry that images can trace and spectra can quantify. The light itself helps tell the direction of the flow. Dust grains, especially those about the size of fine smoke, are excellent at scattering sunlight forward. When the geometry aligns, when the sun, the comet and the observer form the right angle, the sunward side of the coma can appear especially bright, not because material is falling inward, but because the dust there is scattering light toward us with unusual efficiency. Forward scattering and sun-facing outgassing overlay one another, a duet of physics and perspective that makes the coma's lopsided glow both inevitable and beautiful. Inside that glow, the microphysics hums. Dust is not uniform. It ranges from compact pebbles to fragile, fluffy aggregates. The larger pieces, heavy with inertia, lift only when gas flow is strong. The tiny specks rise easily and sail far, pushed by sunlight itself. Water vapour expands quickly from the vents, cooling as it goes, and the velocities, though modest by cosmic standards, are enough to spread a shell of molecules around the body in a matter of minutes. The densest part hugs the sunward side where the sources are, then thins into the anti-solar tail, where radiation pressure stretches dust into a gauzy streamer pointing away from the light. In the spectra, water speaks several dialects at once. There are bright row vibrational lines that flare up as molecules are excited and then relax, and there are broad shallow features that reveal sunlight bouncing off icy grains. Instruments can measure both, and by comparing them tease apart ice on grains from vapour in the coma. When the lines strengthen but the ice signatures in the reflected light fade, it can mean the grains have lost their ices and become dry travellers. When both strengthen together, it hints that fresh icy dust is being lifted, perhaps because a cliff face has collapsed a little, or a crack has widened, exposing new material. The shape of those lines whispers about temperature and motion. A line just a touch broader can imply warmer gas or faster expansion. A slight shift in its centre, towards shorter or longer wavelengths, can betray a gentle bulk flow along our line of sight, maybe from a jet angle toward or away from us. With careful modelling, those subtleties become numbers, production rates, temperatures, speeds. From numbers come patterns, how the water outflow scales with sunlight, how quickly it responds after sunrise on the nucleus, how activity lingers into the local evening as warmth stored in the skin continues to feed a tender wind. Beneath everything is the question of texture, how the surface and subsurface are arranged. A low inertia material, powdery and porous, heats and cools quickly. That kind of surface makes a sharp day-night contrast, vigorous sunward exhalation that quiets quickly when the patch rotates into darkness. A denser, more cohesive crust stores daytime heat and releases it slowly, smoothing the rhythm and feeding a twilight breeze. Water's behaviour helps us decide which story this comet is telling. If the coma's sunward asymmetry is strong and flickers with rotation, the surface may be more like talc and ash. If it is gentler and more sustained, the crust may be firmer, with heat seeping a bit deeper before turning back into sky. There is a deeper tail in the way water and carbon monoxide thread through the same space. Carbon monoxide, more volatile still, can emerge from colder layers or from icy grains lofted high. When CO traces a wider, more diffuse distribution, while water clings closer to the active fans, we learn that the two are not sourced identically. That difference is a map, sketched in invisible ink and revealed by light. One reservoir close to the sunlit surface, another tucked into the cooler places, both singing into the same quiet air. None of this requires violence. The sunward exhale is not an explosion. It is the soft logic of physics playing out in slow motion. Even outbursts, when they happen, are often just a patch of crust giving way, a trapdoor opening on a store of ices that were waiting for the smallest change. The plume surges and then settles. The coma brightens and then returns to its baseline. Through it all, the telescope keeps time and takes notes, one spectrum after another, one image after another, building a diary of the comet's days under a new sun. What makes this discovery tender and important is that water is the most familiar of ices to us, the one we taste and touch and carry. To see it awakened in a body from elsewhere is to watch a universal script unfold. Sunlight, surface, breath. The lopsided sunward glow is simply the geometry of that script. The way a body tells you where it hurts and where it heals, where it wakes first and where it sleeps a little longer. In the quiet of night, as you imagine that brightened crescent around a tiny turning world, you can feel the simple kindness of it. No danger, just information. No drama, just todas detail. An exhale in the direction of the star that, for a brief moment, is warming a traveller from far away. And when the comet moves on, when its sunward fan dims and the tail loosens into darkness, the memory remains in the lines and images we saved. We will know that water was there as ice and as vapour, that sunlight shaped its release into a gentler symmetry, that the coma's glow leaned toward the day like a flower. We will know the cadence of its breath, the way it answered heat, the way it carried pieces of itself into space to be measured by distant instruments. These are small truths, but they are lasting. They fold into the larger understanding of how icy worlds behave, not only here, but everywhere. And for a visitor from another star, that is the sweetest gift it can leave behind. A clear, sunward signature in our books, and a feeling as you drift towards sleep that you have witnessed something subtle and kind. On some nights, the comet looked ordinary, a dim, soft blur wrapped around a darker heart. And then, under especially dark skies, the colour began to whisper through, a pale, ethereal green, as if someone had traced a halo with phosphorescent brushstrokes. Cameras saw it first, stretching their exposures long enough to collect what our eyes can't hold in a glance. The glow wasn't a trick of the lens or a spill of city light. It was real chemistry speaking in visible light, telling a subtle story about carbon and sunlight and the fragile molecules that come alive in the cold. That green comes from a simple fragile molecule, dicarbon, 2 carbon atoms bound together. In comets, dicarbon doesn't usually leave the nucleus ready-made. It's born in the coma, the little atmosphere around the comet, after sunlight breaks apart more complex carbon-bearing molecules shed by the surface. Think of sunlight as both a lamp and a sculptor. Its ultraviolet photons chip at parent molecules like acetylene or ethane, and perhaps organics embedded in dust. And the fragments reassemble as carbon. When these C2 molecules are bathed in sunlight, they fluoresce in characteristic bands, called the swan bands. Clustered in the green part of the spectrum, that is what the camera finds. Not a painted surface, but a cloud of newborn molecules singing in green. And here is the oddity that made astronomers tilt their heads. Earlier measurements hinted that the comet might be poor in the usual carbon chain parents, at least at the moments and wavelengths those instruments were listening. How then could there be such a gentle emerald breath? There are several kind answers to that question, and each adds a layer of calm understanding. The first is timing. Comets are not steady lamps, they are turning worlds. As the nucleus rotates, different patches warm and wake. A region that is quiet one night can bloom the next, exhaling a new mix of gases that changes the balance in the coma. If the green glow was caught during a spell when carbon-rich material was newly exposed, or when a particular vent faced the sun just so, then an apparent mismatch with the earlier spectra is not a contradiction. It's a snapshot taken at a different beat in the same slow rhythm. The second is geography, writ small. Spectra and images do not always look at the same place, in the same way. A spectrograph slit can be narrow, sampling a thin stripe across the coma near the nucleus. If the dicarbon is being created a bit farther out, born from dust grains that drifted away and then released their cargo, or from parents that survive a short distance before sunlight breaks them, an early spectrum that hugged the core could miss the green-making zone. A wide-field image, on the other hand, patiently collects light from that broader shell, and the subtle colour emerges. Same comet, same chemistry, different sampling of space. The third is the hidden pantry of the dust itself. Cometary dust isn't just inert grit, it can carry complex organics locked into fragile, sooty structures. As sunlight warms these grains, or as they collide and crumble, they can feed the coma with the ingredients that photochemistry turns into C2. In that scenario, the green glow becomes a distributed phenomenon, less about jets from the nucleus, more about what happens to dusty breath once it leaves home. You can picture a quiet, slow alchemy unfolding a few hundred or a few thousand kilometers from the nucleus, the green brightening like a soft ring around a candle's core. There is also the matter of what the green is not. It is not the tail itself. The same sunlight that excites dicarbon also breaks it apart, and that destruction happens quickly enough that C2 rarely survives far down the tail. This is why the green tends to gather around the head of the comet, and why the tail often looks white or bluish in long images. Blue comes from different species, like ionized carbon monoxide or cyanogen, whose emissions live at shorter wavelengths. The head glows green, the tail, pushed away by sunlight, carries a cooler palette. It's a gentle, built-in separation of colour by physics and time. Subtler still, there are other greens in nature that tempt confusion. Earth's aurora shimmer with a green line from excited oxygen atoms. Comet Comae can show the oxygen line too, when water and carbon dioxide are photodissociated and leave behind excited oxygen. But in most comets, the sustained soft green that fills photographs is dominated by the swan bands of dicarbon, a broader, richer pattern than a single line. Astronomers disentangle these contributions by looking at the spectrum's fine structure, where the brightness rises and falls across colour with a fingerprint-like regularity. Even the way the glow changes with distance from the sun is informative. As the comet drifts inward, the rate at which sunlight sculpts parent molecules rises. If dicarbon is fed by dust, then nights with stronger dust lifting can yield a thicker green shell. Nights with calmer dust can leave it thin and pale. A small outburst, just a slump on a cliff face, or a crack that widens by an inch, can briefly paint the coma brighter, then let it fade again. Like a sigh you can see. Long sequences of images trace this breathing, and when they are paired with spectra, the puzzle pieces click more snugly into place. Cameras add another layer of clarity through colour filters. Take one image through a filter centered on the C2 bands, and another through a nearby filter that samples mostly dust continuum light. Subtract the two, and the green-making molecules step forward, freed from the dust's reflected sunlight. Do the same for CN or for other species, and you can make chemistry maps, quiet cartography of a cloud. In those maps, the dicarbon sometimes forms a roundish halo. Sometimes it hints at gentle fans that align with active regions on the rotating nucleus. The shapes are never perfectly sharp, physics smudges the edges, but even the smudging carries meaning about lifetimes and speeds. Why does any of this matter for an interstellar visitor? Because the green glow is a tracer of carbon chemistry that began far from our Sun in another protoplanetary disk. If 3I Atlas reliably shows C2 in its coma, it means its ices and dust hold or held parent molecules that release carbon fragments under light, either classic small hydrocarbons or complex organics in dust. If, on the other hand, the green is intermittent or weak, it may hint at a composition depleted in those parents. Neither answer is disappointing. Each becomes a point in a tiny but growing catalogue of interstellar comet chemistries, alongside the water, carbon dioxide and carbon monoxide that infrared instruments track so well. This is where space-based and ground-based observations hold hands. The green lives in visible light, where the big space observatories tuned to the infrared do not usually look. Ground telescopes under dark skies can read those swan bands exquisitely. Meanwhile, space telescopes peel back the veil on gases that Earth's atmosphere hides. When both sets of eyes watch together, we get a layered biography. Infrared for the primary volatiles, optical for the photochemical children like dicarbon and cyanogen, and images to show where they all drift. There is an aesthetic sweetness to it too. Colour is an emotion as much as a measurement. The mind relaxes at the sight of that soft green, intuitively understanding that it means active, but gentle. Light, stirring chemistry, not violence. Even for the scientists who live inside the data, the first time a processed frame shows a round, jade-tinted haze, there's a quiet intake of breath. The universe is being legible again. It is writing in a colour we can love without anxiety. And the apparent contradiction, the earlier hint of carbon chain scarcity paired with this later emerald ring, becomes, with patience, a parable about how truth in astronomy is often a composite, moment by moment, place by place, instrument by instrument. What you see depends on when and where and how you ask. A single observation is a word. A season of observations is a sentence. Only together do they become a story. In that story, the green is not an argument. It is an accent. Evidence that carbon, even if quiet at first, found a way to speak when the time and geometry were kind. If you step outside on a truly dark night and imagine the scene, it helps to slow everything down. Picture the nucleus turning, a rough, blackened stone the size of a small mountain. Sunlight touches one face. Dust lifts like fine smoke. Invisible molecules slip free. A short distance out in the emptiness, the fragments meet light and rearrange. A colour blooms that no one painted, a whisper of emerald that cameras can cradle. Far away, in a room lit only by screens, someone smiles at a plot, someone else adjusts a filter wheel, and another person writes "Green sea too strong tonight" in a lab notebook they will keep for years. Later, when the comet has passed its warmest day and starts its long, slow fade, the green dims with it. The swan bands soften, then sink into the noise. Dust thins, the halo contracts. None of it is loss, it is cadence, expected and kind. What remains are the records, spectra like fingerprints, images like diary entries, all pointing to the same delicate truth. That sunlight can turn invisible exhalations into colour, and that in this visitor from another star's nursery, carbon found its voice as a gentle glow. As you let that image float in your mind, the smallest chemistry writing green on the dark, let your breathing match its pace, unhurried even, and calm. Every interstellar comet is a small courier from a distant workshop, carrying clues in the only languages it can speak. Light, dust, gas and motion. We cannot open it, we cannot hold it, and yet, with patient measurements, we can read where it likely formed, what it has endured, and how different another star's nursery might be from our own. That is the quiet power of a visitor like this. It doesn't just pass through, It leaves a trail of evidence that lets us compare planetary systems the way naturalists once compared islands, by carefully noting what thrives, what is missing, and what patterns repeat. Start with the simplest clues. Which ices wake first? Water, carbon dioxide, and carbon monoxide each sublimate at different temperatures. When a spectrum shows carbon dioxide stepping forward early and confidently while water grows more slowly, it points to a birthplace colder than the zones where many of our comets likely took shape. In a protoplanetary disk, temperature falls with distance from the star, and ice lines mark where specific vapours freeze onto grains. A carbon dioxide-rich breath hints at assembly out beyond the waterline, nearer the carbon dioxide shelf. That is not just chemistry, it is geography, an address written in ratios. The dust adds a second layer of address. Grain sizes and how they scatter light tell us about the material's texture. Fine, fluffy aggregates brighten the coma differently than compact, older grains. If the coma's sunward side looks especially forward scattering, we infer an abundance of very small particles lifted gently by gas. If the spectrum shows the warm glow of larger grains radiating in the infrared, we know some heavier pieces were lofted too. Put together, the dust-to-gas ratio becomes a practical fingerprint. Was this object packed with volatile ices that fling dust easily? Or is it more reluctant, holding a tighter crust that releases only when warmed deeply? Activity patterns sketch the surface without ever resolving it. A lopsided sun-facing plume that waxes and wanes with a steady period whispers rotation and patchiness. It tells us that vents and pits are not evenly spread, that one hemisphere may host CO2-rich sources, while another contributes more water later in the day. When the brightness rises gently after local sunrise on the nucleus and lingers into the evening, we learn about the thermal inertia of the skin. Powdery surfaces respond quickly, cohesive crusts store heat and exhale slowly. Even a faint jet, traced in the inner coma, is a thread leading back to a particular crack or cliff. From those threads, modelers can estimate the nucleus's spin state and the tilt of its seasonal light, then test how sunlight migrates across the terrain during this brief visit. Photochemistry turns the coma into a slow laboratory, and its colours are data. A soft green halo from dicarbon says that carbon-bearing parents, perhaps small hydrocarbons, perhaps organics bound into dust, survive long enough to drift from the nucleus before sunlight sculpts them into C2. If the green strengthens when dusty outflow rises, dust is likely the pantry. If it brightens even when dust is calm, gas jets may be feeding it more directly. Either way, the presence or absence of that colour helps classify the carbon budget of material born under a different sun. The blue of ion tails, the red-brown of dust, the quiet oxygen line from broken water, all together become a palette that, once decoded, maps chemistry to distance, lifetime and source. Sometimes the missing notes matter most. If an instrument sensitive to familiar comet molecules finds them weak while CO2 stands tall, that silence is a clue, not a contradiction. It might mean radiation in interstellar space hardened the outer layers, pruning certain chains while leaving others. It could mean layered storage, a top veneer rich in one ice over deeper pockets of another, so the first days of warming emphasize one voice and later days bring in the rest. Time then becomes part of the experiment. Watching ratios evolve over weeks lets us separate what this comet is from which cupboard door happened to open first. Motion itself is a teacher. The way gas lines broaden and shift gives temperatures and outflow speeds. The angle and curvature of dust tails reveal the push of sunlight and the sizes of grains being carried away. Subtle periodic brightening hints at a rotation period. A changing phase angle with the sun lets us measure how the coma scatters light from different directions. These are not dramatic spectacles, they are careful repeating measurements, and in their repetition lies the comfort of truth. When independent teams using different telescopes arrive at the same production rates and periods within their uncertainties, the comet's behaviour stops being a story we tell and becomes a story it tells us. All of these clues loop back to formation. In disks around young stars, solids grow by colliding and sticking, then migrating. Giant planets stir the architecture, opening gaps, tossing icy fragments outward, and occasionally ejecting them all together. An interstellar comet is likely the survivor of that rough childhood. Small enough to be thrown, strong enough to stay intact, icy enough to speak when warmed by any star it passes. Its CO2:H2O:CO recipe remembers the temperature of the shelf where its grains were stored. Its organics remember the radiation field that baked them. Its porosity remembers how gently or violently its building blocks came together. When we place those memories beside our own comet's memories, we start to see whether other systems favour colder pantries, different carbon chemistry, or more aggressive scattering. Even what the interstellar crossing did to the surface is a clue. Years in the thin rain of cosmic rays can redden and darken the skin, seal pores with processed crust, and trap gases beneath. A first brush with sunlight at just the right angle can crack that shell and release a plume unusually rich in one component. If later measurements show water catching up as the thermal wave sinks deeper, we learn that the CO2 sat closer to daylight, the H2O a little farther in. If instead the CO2 dominance persists, it may be telling us the bulk composition is genuinely different, not just layered, but born that way. There are dreamier clues that sometimes become practical. Isotopes, like the ratio of deuterium to hydrogen in water, carry the signature of their natal temperatures even more strongly than bulk abundances do. When instruments are sensitive enough to set limits on these ratios, they add a sharper contour to the map of origin. Colder birthplaces tend to elevate D/H. Even when a specific ratio is beyond our reach for a faint visitor, the possibility anchors the logic of future missions and measurements. The same is true for noble gases and other tracers that, if caught, would sketch pressure and temperature at the moment ice is locked in. Comparisons among the only 3 interstellar visitors we've met so far already tell a cautionary, hopeful story. There is no single template for material from other systems. One had little to no visible coma, another behaved like a familiar water-rich comet, and this one breathes with a distinctive CO2 accent and a sunward lopsidedness. That small sample, diverse as it is, argues for variety in disk structures and histories. Different distances of ice lines, different carbon to oxygen balances, different arrangements of giant planets doing the scattering. In other words, the recipes for building worlds are not all the same, and these messengers let us taste the differences. The telescope's role in all of this is to turn faintness into legibility. Infrared spectra cut through the veil of Earth's atmosphere to read CO2 cleanly, while ground-based eyes trace visible emissions and tail shapes with wide fields. Together, they translate light into numbers, production rates in molecules per second, grain sizes in microns, temperatures in tens of Kelvin, periods in hours. Those numbers feed models that test origins. If the CO2/H2O ratio is this, and the dust behaves like that, what disk temperature and pressure reproduce it? If the coma map shows water sourced close in and CO2 more extended, which layering fits? The answers are rarely single points, they are gentle ranges, but even ranges can prune whole families of possibilities. Beyond the specifics, there is a broader comfort in what interstellar comets teach, that the physics of sunlight on ice, of gas-dragging dust, of molecules glowing under starlight is universal. A body born under a different star still responds to this sun in ways we can predict and measure. That universality lets us use one momentary visitor to test ideas about many unseen systems. And if someday we build instruments to touch the comae of these travellers more directly, scooping dust, sampling gas, the quiet groundwork laid by careful remote sensing will tell us where to look and what to ask first. For now, the clues we gather fit together like a patient puzzle. A CO2 forward spectrum suggests a colder nursery or a layered crust. Water lines arriving with a sunward asymmetry trace active patches and thermal inertia. A green glow from decarbon ties the dust to carbon chemistry farther out in the coma. Tail geometry, line shapes, and brightness rhythms supply speeds, sizes, and spins. Lay those pieces on the table and a picture forms of a small world that likely assembled far from its native star. Was tossed into the dark by larger neighbours, weathered the interstellar drift, and now, just for a while, breathes in a new sunlight that lets us read its past. It is a gentle kind of science. Nothing is hurried, nothing is forced. We let the comet turn, we let the ratios change with the day, we record, compare, and refine. And as you listen to this, relaxed and unburdened, you can imagine those clues settling into place, one spectrum, one image, one quiet realization at a time, until an object that began as a faint moving dot becomes a small, clear statement about how other planetary systems build and scatter their icy things. That statement is enough to carry you towards sleep. The universe is varied, but it is understandable, and even a single traveller can show us the map. Across the turning Earth, night hands the baton from one observatory to the next. A dome closes in Hawaii as a shutter opens in Chile. A camera warms in South Africa, while a spectrograph settles in Spain. The comet never waits, so the world learns to move with it. Schedules flex, ephemerides update, and the sky's slow choreography becomes a relay in which each instrument contributes a different note. Composition here, structure there, timing everywhere, until the quiet visitor is not just seen but understood. High above the warmth and weather, the space-based eye listens for chemistry that the air below would muffle. It rides along with the comet's motion, gathering spectra in the infrared where ices speak most clearly. The light, split into delicate bands, reveals which molecules are waking. The sure signatures of carbon dioxide, the gentler tones of water, the whispers of carbon monoxide and other volatiles. From those lines come production rates and temperatures, the daily breath of the comet written as numbers that can be compared from week to week. On the ground, the great mirrors take their turn. They track the comet non-sidereally, ever so slightly off the star's rhythm, keeping the nucleus centered while the background smears into soft streaks. With high-resolution optical spectrographs, they comb the visible light for narrow emissions. The cyanogen that etches a thin blue, the swan bands of dicarbon that tints the coma green, the faint oxygen glow that follows broken water. When the air is steady and the optics are kind, those instruments separate neighbouring lines that would otherwise blur, turning a fuzzy halo into a ledger of species and speeds. Line widths hint at the temperature of the gas. Tiny shifts reveal the flow along our line of sight. A forest of weak features, stacked and averaged, becomes a chorus you can trust. Images with wide fields give the comet its silhouette. They lay out the coma and tail in a single frame, then return again and again to watch how those shapes evolve with sunlight and rotation. Narrowband filters isolate one molecule at a time, dicarbon here, cyanogen there, while continuum filters measure dust alone. Subtract one from the other and the chemistry steps forward. Faint fans aligned with active regions, a rounder envelope where photochemistry is at work, a ribbon where ions are swept into the solar wind. Polarimeters add a subtle dimension, probing how dust grains scatter and align, teasing out whether the grains are compact or fluffy, young or processed, smooth or ragged. Even the way the brightness falls with distance from the nucleus, the radial profile, carries information about how quickly grains are launched and how fast they drift. Survey telescopes sweep the sky like metronomes. Their strength is cadence, short exposures, repeated night after night, that nail down position and brightness with machine patience. Every new measurement refines the orbit and tightens the ephemeris. Every light curve stitched from those points hints at a rotation period, a gentle brightening, a sudden lull. If the comet hiccups, an outburst, a small collapse, a vent that opens, these surveys are often the first to notice, flagging a change that sends bigger instruments pivoting for a closer look. The flow of discovery notices and observing alerts becomes a soft global heartbeat. A message goes out. Telescopes listen. Data come back. The message changes. We listen again. Radio and millimeter observatories try their quiet work when geometry and brightness allow. They tune to rotational lines of simple molecules, listening for the cold music of carbon monoxide, formaldehyde, hydrogen cyanide, or the long wavelength echo of OH, an indirect tracer of water. The detections when they come feel like catching a distant conversation through static. The non-detections are as instructive, setting upper limits that fence in the comet's recipe. Submillimeter arrays can even map where a species is densest, drawing a faint, invisible weather map across the inner coma that complements the infrared and optical portraits. Not every telescope needs to be huge to matter. Modest instruments, half-meter mirrors in quiet backyards, 1-meter university scopes under dark plateaus contribute time that the giants cannot spare. They measure total brightness through standard filters, track the steady fade and flare, and send their results to shared databases where professionals and dedicated amateurs mingle. A dozen small measurements added together can pin down a light curve phase that a single giant missed because clouds rolled in or a schedule shifted. In this chorus, the smaller voices keep the rhythm. Coordinating all of this looks more like weaving than commanding. Teams share finder charts with non-sidereal rates and tiny offsets for dithers. They agree on apertures for photometry so that numbers from different nights can be compared without argument. They post reductions and quick-look spectra as soon as they're clean enough to be trusted, inviting others to confirm and extend or gently correct. When a pattern emerges, CO2 steady while water grows, dust production breathing with a 10-hour beat, someone turns that pattern into a simple forecast. Look here, at this hour, with this filstro, you might catch the plume. Around the planet, domes and instrument rooms become quiet rooms in the same house. From this fabric of data, the comet's behaviour becomes a set of linked stories rather than isolated facts. A green halo intensifies on nights when dust is abundant, suggesting that dicarbon is being born from parent molecules carried by grains. The sunward coma stubbornly outshines the opposite side even when viewing angles change, implying genuine asymmetry in active regions rather than a trick of scattering. The tail kinks ever so slightly when the solar wind shifts, a reminder that ions are yoked to an invisible weather none of us can feel. A faint jet rotates in and out of view, lending a steady pulse to the brightness that matches the suspected spin period. Numbers check numbers. Images explain lines. Lines anchor images. There are moments of serendipity that only a network can catch, and a small observatory notices a subtle brightening right after local dawn on the nucleus. Hours later, a larger telescope, now at night half a world away, finds stronger water lines than the night before. The connection is tentative and then obvious. The surface warmed just enough to wake a new patch. Another night, a millimeter dish places an upper limit on carbon monoxide so low that modelers revise their assumptions, and, in response, an imager chooses a different pair of filters to chase dust rather than gas. The plan flexes. The comet does not care, but the science improves. Even the way data are archived feels musical. Raw frames, calibration files and reduced products slip into public vaults where anyone with patience can rework them. Someone stacks a month of wide-field images and recovers a dust streamer too thin to see in a single exposure. Someone else fits gas line ratios with a different radiative transfer model and nudges a temperature estimate by a few degrees. These small refinements sand down the roughness until independent paths arrive at the same smooth shape. What began as disparate melodies resolves into harmony. If you could stand outside all of it and watch the night from above, you'd see a pattern repeating every 24 hours. Sunset, dome slit, a brief hush, then the muted clatter of an instrument coming alive. Hours later, a handoff across an ocean. Later still, a different wavelength taking its turn. In between, meetings where voices from 6 time zones share screens full of spectra and profiles and the simple pleasure of a clean fit. No single telescope could tell this story. It takes the whole ensemble, space-cold optics and warm mountain air, giant mirrors and small faithful eyes, filters and gratings and dishes to turn a travelling spark into a portrait, and as the comet rounds its bend and begins to dim, the chorus quiets by degrees. Instruments that needed brightness step back first. The wide fields linger, following the last breath of dust until it sinks beneath their thresholds. Radio dials go silent. The space-based spectrograph turns to another target. What remains is the score. Time-stamped lines and images that, read in order, play back the performance anytime we wish. It is a gentle kind of completeness. We did not hold the comet. We held hands around it, each voice adding what it could, and together we learned what the visitor chose to tell. Now the domes close, the screens dim, and the Earth keeps turning. Somewhere between stars, the traveller continues. Here, the music fades into memory that you can carry into sleep. What makes this visitor stand apart begins with the simple fact that it is the third of its kind we've ever seen, only the third known object to wander into our skies from another star. With just 3 examples, each difference matters. The first, the one we named for a scout, looked like a shard of something long-weathered. No visible halo of gas, no obvious tail, and yet a puzzling push that didn't fit gravity alone. The second behaved like a textbook comet. Steady activity, a bright coma, a clean tail, reminding us that space between stars can deliver something familiar. This one, though, speaks in a new accent. It is active, yes, but its breath is unusually rich in carbon dioxide. Where most comets near the Sun are led by water vapour, here the carbon dioxide lines step to the front with confidence. That chemistry seen clearly is the first signature that sets it apart. There is also the way the activity presents itself in space. The glow leans toward the Sun, not as a sharp spear, but as a soft sun-facing swell. That asymmetry tells us about the surface, about patches that wake in daylight, about vents that open and close with rotation, about tiny landscapes we cannot see directly but can sketch from behaviour. The sunward exhale is not unique among comets, but paired with the carbon dioxide emphasis, it becomes a specific fingerprint. A cool nursery composition voiced through uneven terrain. If the earlier visitor without a coma was a riddle, and the second was a reassurance, this one is a lesson. Gentle, detailed and new. What truly makes it special is the timing of our tools. When the first traveller arrived, we did not have a cold, steady eye in deep space tuned to the infrared fingerprints of ices that Earth's air tends to hide. Now we do. It means we are not guessing at carbon dioxide, we're reading it directly. We are not inferring water only from secondary products. We are seeing the lines themselves. That clarity turns differences into measurements rather than impressions. It lets us say with care that this object's early breath is led by volatiles that stir sooner, at lower warmth, and that water follows as the heat wave seeps a little deeper into the crust. The comparison across the 3 visitors becomes a quiet map of possibilities for other solar systems. Imagine 3 messages from different workshops. The first says, it's possible to send out fragments too dry or too processed to light a visible coma, yet still light enough to be nudged by some subtle outgassing or other force. The second says, a classic comet can be ejected from another star's pantry carrying ices and dust that behave much like our own long-period visitors. The third says, change the pantry's temperature or the layering of its shelves and you can build a body that wakes with a carbon dioxide-led voice, in a way we rarely see dominate so clearly here. With just 3 samples, variety already feels like the rule, not the exception. Composition is only part of the difference. Pacing is the other. This object's story unfolds as a sequence. Carbon dioxide first, water joining, dust following along. The order and the ratios are clues to depth and structure. A thin, processed rind over fresher stores, or simply a bulk mixture that favours one volatile over another. The earlier, comaless visitor gave us shape and motion but little chemistry. The second gave us chemistry that matched the familiar score. This one lets us watch a new solo line rise and then harmonise. In a small catalogue, that sequence is precious. It tests our models of how ices arrange themselves in small bodies and how Sunlight teases those layers into the open. Even the colour, when it appears, adds to the distinction. A faint green halo built by decarbon tells us that carbon-bearing parents, perhaps in dust, perhaps in gas, are being sculpted by light into molecules that fluoresce in the visible. That glow can strengthen when the dust lifting grows, hinting that the pantry for those parents may be grains rather than vents. For the second visitor, the green lived inside a more ordinary mix. For the first, it never appeared at all. Here it arrives as a counterpoint to the infrared message. Carbon dioxide leads in the infrared. Decarbon adds a soft echo in the visible. Two corners of the spectrum, two ways of saying carbon is available, and together they sharpen the picture. Another way this traveller stands out is practical. We caught it in time, and we caught it together. Space-based spectroscopy reached for the delicate bands that air would hide, while ground-based observatories map the coma's shape, the tail's angle, the colours and line widths that trace temperatures and speeds. That overlap means we can line up the when and where of different signals. When the sun would swell his brightest, do the carbon dioxide lines hold steady or surge? When water strengthens after a rotation, does the green halo respond in step? The answers turn different into diagnostic. The first visitor arrived before we knew how to organise such a chorus. The second taught us the rhythm. This one benefits from the full ensemble. It is tempting to call out the mystery of the first object's gentle, non-gravitational push and say that nothing will ever be stranger. But strangeness is not a contest, it is a catalogue. The puzzle of a force without a visible halo suggested exotic ideas and also simple ones, from unusual outgassing to geometry and reflectivity. The steadiness of the second visitor argued for the commonness of certain recipes across the galaxy. The carbon dioxide forward breath of this third is another kind of strangeness. Less dramatic to the eye perhaps, but just as meaningful, because it points to temperatures and pressures in a distant disk, to ice lines set at different radii, to the way giant planets there may have stirred and scattered their small icy neighbours. Think of what that implies for planet making elsewhere. Shift the ice lines inward or outward by a little, and the ingredients available to build comets, and then forward to planets, change quietly but significantly. Favour one molecule over another in the easiest to freeze category, and the chemistry that seeds young worlds adjusts. A body tossed out of such a kitchen and sent wandering between stars will carry that bias like a passport stamp. Catch it with sunlight and you can read the stamp from the glow. This is the heart of why the object is special. It is not just different. It is legibly different in a way that talks about origins. There is a gentleness to its uniqueness that matches the tone of a sleepy documentary. Nothing here requires drama. The comet does not break apart in spectacular fashion. It does not sweep close to Earth. Its tail is not a blazing sword. The specialness is in the details, the order of which gases speak when, the angle of a lopsided coma that points toward day, the quiet green that comes and goes with dust, the way production rates settle into patterns that instruments on different continents can all agree on. It is science at a slow heartbeat, patient, careful, cumulative, and that pace is part of the gift. You can feel the contrast if you picture the three travellers side by side. One is a muted stone gliding through with hints and riddles. One is a classic, its bright breath and graceful tail telling a familiar tale, only with foreign ingredients. And one is this, a visitor that wakes in an unusual register, carbon dioxide forward, water following, the sunlit face puffed just a bit more than the night side, as if bowing politely to the star before it moves on. In that still life, diversity stops being an abstract claim and becomes a view you can hold in your mind. 3 ways for small things to be made and to behave when warmed, 3 results from 3 nurseries we will never see directly. What also makes this one stand out is how it refines our instruments for the next time. By measuring a strong carbon dioxide signal cleanly, we learn which exposure times and settings bring out faint features best. By watching how the coma's asymmetry maps onto rotation, we learn how to schedule observations to catch the same patch of the nucleus in daylight on different nights. By pairing visible light chemistry maps with infrared lines, we learn how dust-borne parents and nucleus-borne gases braid together. Those lessons will make the fourth and fifth visitors feel less like mysteries and more like old friends we know how to greet. In the end, the specialness is not a single headline. It is a bundle of quiet differences that add up to a new shape in a tiny collection. A carbon dioxide-led breath, a sunward, lopsided halo, a cooperative era of instruments that can read both clearly, a colour that flickers with dust, a safe, distant passage that lets us watch without hurry. Taken together, those features say something simple and large. Other planetary systems do not just echo ours, they rhyme with it in varied ways. This traveller brings one of those rhymes. As it fades and the records take its place, that rhyme will stay in the book, a gentle line in the poem we are slowly writing about how worlds are made. Close your eyes and it's easy to hold the difference without clutching it. Just a soft understanding that the universe has more recipes than we thought, and we are finally starting to taste them. The end of the visit arrives without ceremony. There is no final flare, no dramatic unspooling. The comet rounds its shallow bend and begins to recede, and the sky answers with a small adjustment. Night by night, the glow softens, the tail thins, the core dims by increments too gentle for hurried eyes. In the mathematics of its path, this is expected, an object on a one-time curve, carrying more energy than the sun can keep, setting its course for the far cold again. In the feeling of it, though, there is a quiet tenderness, as if a lantern carried down a distant path has turned a corner and begun to fall out of sight. The physics of departure is simple and soothing. Sunlight that once struck the surface steeply now arrives from a changing angle. The nucleus, still rotating, presents those same scarps and pits to a gentler, cooler day. The thermal wave that had seeped centimetres into the crust loses momentum. Ices that once woke easily in the new warmth settle back. Gas production drops. Dust lifting slackens. The coma that had leaned toward the sun relaxes, rounding a little as the strongest plumes calm. The tail, always pointing away from the sun rather than trailing behind the motion, pivots to keep its quiet allegiance to light, and then length becomes the only drama left. A pale streamer stretching into the dark, thinning like breath in winter air. Even as the light fades, the geometry keeps giving small gifts to those who watch. The changing phase angle, the triangle between sun, comet and Earth, alters how dust scatters. Some nights the forward scattering makes the sunward side glow more than expected. Later, at a different angle, the glare softens and the outer envelope reveals itself more evenly. Telescopes that once needed short exposures to avoid saturating the inner coma now lengthen their gaze to pull out the faint outskirts and the tail's finer filaments. What looked like a single tone at the crescendo resolves into harmonics during the diminuendo. Subtle striations from dust released at different times. A faint kink where solar wind conditions shifted. A narrow spike from a jet that kept breathing even as the rest quieted. Inside instrument rooms and on quiet mountaintops, the observing plans changed their rhythm to match the comets. Spectrographs that had focused on strong gas lines switched to integration strategies that stack many long exposures, coaxing signals from the noise with patient arithmetic. Photometric campaigns widen their apertures to capture more of the weakening glow. Then, when the practical limits approach, narrow again to follow just the inner coma as long as they can. Wide field images give the last looks at the tail's architecture, a dust fan that thins to transparency, a ghost of an ion tail sketched along magnetic field lines, an almost imperceptible envelope that under deep stacking still holds shape. Eventually instruments that need brightness bow out one by one. What remains for a while are the faithful small telescopes and the eyes that love them, holding the thread until it too slips past reach. The data do not dim. If anything, they grow brighter in meaning right now, when the flow slows enough for everyone to sit with it. Raw frames, calibration sets, and reduction scripts circulate through teams like sheet music after a concert still warm from use. People who have been awake at the wrong hours for weeks sleep a little more and then return to their screens with gentle minds. Lines are remeasured with tighter baselines. Production rates are recomputed with new error bars that reflect the whole arc, not just a night or two. The ratios that seem surprising in the beginning are set within a curve. Here is where carbon dioxide led. Here is where water joined. Here is where dust production breathed with rotation. Here is where it all began to settle. The uncertainties that were generous when the visitor was bright and lively narrow into numbers that feel like statements rather than conversations. One of the sweetest parts of the exit is comparison. With the frenzy of catching new behaviour behind them, observers take the time to cross-check. Infrared lines from one facility are plotted against visible emissions from another and against broadband brightness from a third, all on a common time axis. Where dips and rises align, confidence grows. Where a line seems to misbehave, the team hunts for causes, calibration quirks, geometry effects, a thin cloud that no one noticed, or perhaps a real delayed response in dust or gas. Each small riddle resolved is a soft click as a puzzle piece seats. The larger picture, that this traveller breathed differently from most of our own, that sunlight teased out an unusual order of voices, that its surface spoke in patches, comes into crisp relief. The models grow alongside the measurements. A rotation period estimated in the excitement of first detection is refined by weeks of gentle brightening and fading. Thermal inertia, once a guess, is constrained by how long activity lingers into local evening on the nucleus. Jets are placed on a notional globe, longitudes and latitudes assigned from the timing of their appearance, and then tested against what the tail geometry and the inner coma asymmetry would look like if those vents were real. Simulations that once had to assume a generic nucleus now get to borrow this one's quiet personality. Not a sphere, not a frenzy, but a modest, lopsided exhale that turned with the day. As the object retreats, practicalities transform into grace notes. The ephemeris, those nightly coordinates that told telescopes where to look, stretches farther into the future than anyone will follow. A neat list of appointments that will be kept by nobody because the guest will be too faint. The archives, which accepted the first raw frames with all their blemishes and urgency, now hold polished versions too, fully reduced spectra with wavelength solutions and flux calibrations, stacked images with careful masks, light curves with uncertainties and comparison stars clearly listed. Someone writes the first draft of a paper, not with fanfare, but with the same pace the comet taught. Method, result, interpretation, kindness to what is not yet known. There is a human quiet to the exit that feels right for sleep. The feeling of "we must catch this now" loosens its hold, replaced by "we did, and here is what it said." People who had been strangers at the start, names on circulars, voices in hurried meetings, have become a small community with a shared, gentle accomplishment. They will go back to other projects, but for a time they were hands on the same thread, passing the relay batons of night and method across oceans and time zones. That linger of connection is part of the comet's wake, as real and as intangible as the dust that will keep spreading along its path long after no one can see it. Far from us, the nucleus enters a colder page of its journey. The exhaust that made the coma becomes rare. The tiny world is again a black stone turning in darkness. Its stored heat spent, its vents quiet, its fractures no longer breathing. Gravity from the sun has done its work and let go. The comet slides into the general night between stars, where starlight is an idea rather than a warmth. It will not remember us. It will carry inside of whatever layers it has left the same chemistry it brought, altered only by a thin crust of experience from this brief season near a foreign sun. We, however, keep a record that outlasts the glow. In the spectra are lines that will be plotted in textbooks and talks. Here carbon dioxide took the lead, here water followed, here dust told on the surface. In the images are tails and halos that will become teaching examples for how scattering and geometry weave appearances. In the numbers are fits and residuals that will discipline the next model that tries to tell us what an interstellar comet can be. And in the minds of the people who watched are small personal memories, moments when a graph on a screen looked unexpectedly beautiful, when a long exposure finished and revealed a delicate structure, when a crude first reduction at 3 a.m. matched a colleague's result from a continent away. Even when the comet is gone to all instruments, a trace remains in the solar system itself. Dust released at perihelion continues on its own paths, widening in space and time into a diffuse band too thin for any one eye to notice, but real enough that somewhere in a quiet future, a spacecraft's dust detector might catch a few of those grains and count them. Most will wander forever unnoticed, as they were content to do before we invented names for their parent. It is a comfort to think that the visitor leaves something of itself behind that is harmless and faint, like a friendly footprint at the edge of a beach. If you hold the whole encounter in your mind, it steadies the breath. A faint point became a halo. Chemistry spoke in order. Dust drew lines in light. The visitor turned, made its shallow bow to the sun, and withdrew. We watched without hurry, wrote without drama, learned without noise. Nothing demanded more of us than attention. Nothing asked us to be brave or clever beyond patience. The universe offered a small, exact lesson. Even across gulfs of dark, small things carry stories. Even brief encounters can be clear. Even departures can feel complete. So let the comet go, let it slide outward along its open curve, shrinking beyond every lens, then beyond every hope of detection, and finally into the ordinary anonymity of space between stars. Here, let the after image be the work we did. A tidy stack of spectra, a handful of quiet images, a few easy sentences that say what was true. There is nothing to chase. There is nothing to keep. There is only the knowledge that a traveller passed, that we greeted it gently and that we understood enough to be satisfied. Breathe in, breathe out, and allow that satisfaction to carry you downward. Like a tide easing off a shore, the night keeps its secrets kindly. The records keep their truths, the visitor keeps on.